Squeaky chair. Okay, so you might be kind of tired of me playing with waves on strings, but I'm going to continue. So I want to look at this beaded string and model it in Python 2 different ways, and it's going to be kind of awesome. Okay, so let's just get started. Oh, so I should say I've already derived some of this stuff. This is part of my ongoing series on strings and waves, and I'll post that stuff down below. Okay, so here we have, is this a video? This is a video, there we go. So here's a Mardi Gras beads. I have 20 grams hanging over the edge of that pulley, and then I flick it, and so you can see the motion of that. Let's just play that one more time. Flick it, and then I can actually find the velocity of that wave on that string, and then model it in Python and get everything to agree, and that's gonna be winning. Okay, so here's the string. Here you can see, maybe my mouse isn't big enough. I guess you can see that. So here's that hanger with the weight over it. That gives the tension in the string, and then I can find the mass of the whole beaded string, and the length is 1.2 meters. So I have the length, 1.2 meters. I have the mass. I have the tension from the 20 grams hanging over the edge, and then I have the linear mass density, which is important in when we talk about these things. So let me give the super brief derivation of the wave equation and how it depends on both the length, not the length. It depends on the linear mass density and the tension. Okay, so this is the derivation I like. Imagine that we have a string like this. It could be differentially small elements, or it could be finite elements like in a bead. It doesn't really matter. But each bead has 2 forces acting on it: tension pulling to the right and a tension pulling to the left. So if I look at this mass label number 2, I have T1, which is the tension pulling to the left due to mass 1, and T3 to the right, mass 3. Now, let's assume, we're going to make some assumptions here, and again, I'm going super fast here because I just want to get to the wave equation. We assume that the mass can only move in the y direction. So the net force, T1 plus T2, T3, there's no gravity, is the mass, which is delta m, because not the whole thing, times the vertical acceleration a2y. So it's T1y plus T3y, right? The y components are all that matters. So I need to get the y components of these forces, so I can use this I can assume that the tension's towards mass 3. So using the position of mass 2 and the position of mass 3, I can kind of get the mass, the y component of T3. So this is delta y is the y displacement, delta x is the horizontal, and s is the distance. So I get this similar triangle for the tensions, right, for T3. And then I make the very rough assumption for small displacements in the vertical direction that s, the distance between the masses, is delta x, the horizontal distance. I know that's a stretch. I know. So then I get this ratio delta s over y is T3y over T, the total tension string, which is constant. So I get T3 is the tension, T, the total magnitude, delta y over delta x. Now, for T3 delta y over delta x, it's going to be y3 minus y2. That's the delta y. Delta x is the same for all the pieces. But for T1, since it's actually pulling to the left, it's T1 minus it's y1 minus y2. Okay. And again, it's y1, y2, y3. Okay, got that. So then I just say the net force, I just add those 2 y components together. I get that. I set that equal to mass times acceleration for element y, which is the acceleration is the second partial of y with respect to t. And then the mass is mu times delta x. Divide both sides by delta x. I get that. So the thing on the left is the second partial of y with respect to x. It is the same. I'm not going to go over that. It is. I've already done that in another video. There's a lot to do here, people. We got to get going. So then if I set the second partial of that equal to mass times acceleration, I actually get this. And this is the wave equation right there. And that is true if v is the tension, the square root of the tension over mu. Boom, wave equation. That was really quick. Okay, now, what am I doing next? I can't remember what I'm doing next. Let's see. Let me look at my cheat sheet over here, because I don't want to surprise myself. Okay, so now let's go back over here, and this is my actual string. So what I did was my video camera is fast enough. I can actually look at the motion of that wave pulse as a function of time and use video analysis. I'm using tracker video analysis. I scaled it with that meter stick, and I can get this position versus time. It works very well, right? The slope of this position versus time would be the velocity, and you can see right there it's 2.85 meters per second. Now, if I go to the theoretical velocity, the square root of t over mu, using my t and my mu, I get 3.07. That's pretty good. I'm pretty happy. Pretty good. Okay, so those are my two velocities. So now what I want to do, I'm going to model this method number 1, and that's using springs. Okay, so if I have a mass on a spring, we can model the motion like this. So there's a couple parameters. Suppose I take the beginning of the spring to the mass, and I call that the vector L. And then I have the unstretched length of the spring. I can call it L0. It's not a vector, it's just a magnitude. And then L hat is the direction of the vector L. Then I would get the following vector force for that one spring. It's going to be negative k, the spring constant, times the difference in the magnitude of L and L0, and then multiply by L hat to make it a vector again. So this is a better version of Hooke's law, but we need that. We can't just write negative ks, right? Because that doesn't even make sense. We need it as a vector. So that's that. Put a box around it. So I'm going to break my string into finite masses connected by springs. So the whole thing has a length L. In this case, I have 5 pieces. I'm going to use more than 5. So the mass of each piece is going to be the total mass divided by the total number of pieces. That makes sense. And so then the distance between each element we can call S. And so S is going to be the total length divided by 1 minus the number of pieces, right? Now, if you have enough pieces, it doesn't matter. If I do 1,000 pieces, 1,999 doesn't matter, but it does matter, okay? So because if you look at right here, I have 1, 2, 3, 4. I only have 4 springs, but I have 5 masses. And then I have the unstretched length is that distance S. If I look at from one mass to the next, I just take the difference in positions to find the vector L. So if you think about each mass on that, it's going to have 2 forces, one due to the spring on the left, one due to the spring force on the right. And I'm going to use this axis, I'm going to use a list. I'll show you this stuff later, and so don't get too caught up in that. Okay, so what about the tension? Because, I want the linear mass density, I can fix that. But what about the tension in the string? I definitely need to set that. So here's my mass with springs connected to it, and imagine that I stretch it. Then I want to kind of quantify that force of stretching. So I'm going to use capital K for the spring constant for the whole string. Okay, and the whole thing gets stretched an amount delta S. I'm not sure about that. I know it works out in the end. I'm kind of, delta S is a stretch for each piece or the total thing. I think it's the total. Yeah. And then but the spring, if I stretch this spring an amount delta S, then I have to consider all of them don't stretch the same amount. That's not delta S. What worked out in the end? So here I have K is the spring constant for each individual one. It has to be a multiple of the total spring constant. But I don't really need the total spring constant. What I do need is the natural length. And this is the trick right here. This is a little trick. So I can set the natural length to some starting length and multiply it by a factor. In this case, I had multiplied it by 0.9. Why? Why would you do that? That means that it's already stretched, right? If I start with it right here and the natural length isn't this total length, then there's already a tension in the string, and that's that tension that I want. So I call this pre-stretch, right? By setting that 0.9 factor in there, I'm actually pre-stretching my whole string, and I can set that to whatever I want. The pre-stretch. I can either change this value or I can change the spring constant, but I can set that constant. So I can use the same tension that I have in my actual real string. And that's kind of cool. So here's how you would calculate the actual tension. And so you could either just guess a value for the 0.9 value to stretch it or whatever and just print it. That's what I do. Okay, so here's the plan. I'm gonna calculate all my values. I'm gonna make all the balls. I'm gonna put them in a list, and I'm gonna use a Python list. I'm gonna show you all the code. I'm gonna show you everything, and then I need to take the ball on the left end and kind of move it up and then back down, and that will start the wave. I don't want to just have I want to reproduce what I saw in the video. Not exactly, but close. Then I'm going to go through, if I know the positions of all the balls, I can calculate the spring forces. And if I know all the spring forces, then that's good. I can use those forces to update the momentum. This is the Euler method of numerical calculations. And then I can use the momentum to update the position. And then I can remove the spring so it looks nice. And then I would do that. Here's how that would look after you calculate the forces. This is the momentum update formula. This is the position update formula. And again, I'm flying through this because I'm just excited. And there's a lot to do. And then update time, and then just repeat this whole thing over and over and over again to get the whole model, the wave thing to work. Okay, so I'm going to show you what it looks like, and I'm going to show you how to get that. So here is my string. These are all masses, and those are all springs connected by it. And then I just shake up that one piece. The wave goes down the string and reflects back, and it jiggles around, which isn't completely realistic for the jiggling, but the question is, does the wave speed agree with reality? And we'll get to that. Let me show you all the parts of the program. So here we go. I cut up the graphing stuff, but so this is just L is the length and the mass and the total spring constant of the string, which I picked. I just picked a value there, which is kind of low. That's fine. And then this is number. I don't know why I picked 34. I can't remember. And this calculates the individual spring constant. Again, that only really matters for the pre-stretch to make it have the tension that I want. Okay, so this stuff right here, this line 24, this is the angular velocity of the pulse. So I set it at 45 radians per second. The A is the amplitude of that pulse, and the TP is the time of the pulse. Because I don't want to just keep on shaking it up and down. I just want to do one shake and then stop. So TP is essentially half a wave, right? I want to go up and back down and stop. B, that was a drag parameter that I turned off, so it's still there. Okay, left end and the right end are just vector locations, so I can set when I start making my masses where to start from. And then ds is the vector distance that I would move based on the number of pieces that I have. R is, it's just a constant, looks like. L divided by, oh, this is the radius. That's the radius of the stuff. So the more mass you have, the smaller B, but it doesn't really matter. Okay, so here's the key. Like when I make all my masses, I'm going to put them as spheres in this list called balls. And so I start off with an empty list of balls right there. And then this line 36, this just adds in balls to the list. So I go for I in range n, so I have n number of balls. I'm going to add to it n times. And then I just add a sphere. The position of each starts at the left, and then I move over I ds, right, where ds is a vector. I give it a radius, I give it a mass, I give it initial momentum as 0, and this is a trick that I like to use. I give it a force. That's the net force on that ball. So I can reference that by saying balls 0.f, and that's the force on that ball. Now I'm going to make the springs. Now this one, remember, there's one less spring, so I go I minus 1, and then it's another list. Cylinder, just it's pretty easy to put them in the right location. They're all the same size and everything like that. And then here's my pre-stretch, that 0.9, you can change that value. T is 0, dt is 0.001. TK, that's just, well, here I did in line 49, I calculated the tension just to check. So I took balls 7 and 8, I just randomly picked two balls. I took the difference between them and calculated the spring force in that one spring. That's the tension in the string, right? That's what I wanted to check and make sure that I was getting what I was thinking I was getting. Okay, so here's the main loop. This is it's going to run for 2 seconds. In GlowScript vPython, yes, I'm going to give you the code. Don't worry about that. Rate tells it to do no more than 5,000 calculations per second. So I'm actually not running this in real time, but that's okay. Okay, line 54 and 55. This is and 56 and 57. This controls that left end to shake it up and down, right? So if the time is less than the time for one pulse, then I give it this A sine omega t displacement in the vertical direction. And then after that time, if it's after that time, I just fixed. So I shake it and I stop it. I hold it. Okay. 58 calculates the force. So here you see I go through all of the middle balls. I don't do the first, and I don't do the last because they're fixed. I don't need to calculate those forces, and which is good because those are different. The ball on the left doesn't have a force on the left. The ball on the right doesn't have a force on the right. So balls I dot F is the force on that particular ball. I'm going to go through all of them. So this first is the springs I minus 1, so it's to the left. And you notice, see, I start at 1, not 0. So I do have a spring to the left. That's the spring force to the left, and I multiply it by a unit vector to make it a vector. And then this one is the spring force to the right. And then that negative B balls dot I dot P, that's that drag force. But I turned it off because B equals 0. You can turn that on and play with it, but I was just trying to make it a more realistic spring, and I should just stop that. Okay, so now in line 61, this is pretty easy. I've calculated all the forces, so I need to update the momentum and update the position. So I just go through each ball, I update its momentum right there, line 62. I update the position, simple as can be. That's pretty cool, huh? Line 65, now I just move the springs. I need to reposition all the springs so they start on the balls, and I need to change the length of the springs. And then I plot stuff that I'll show you how to do that in just a second. Okay, so what if I want to look at the wave speed of that pulse? So what I need to do is to find, I have all of these balls have different x positions, but I want the x position of the peak as it moves down that string. So this function that I made, max xy, finds the x value of the maximum y, right? So it's the top peak. So all I do is just set these two to 0. I go through my list of values and I find the one that has the greatest y value, and I return the x value of that one. So that's what that is. And then so I can graph that. I make a graph, I make a function to graph, and then that's it. And here's what I get. This is the position of the peak. And then if you use Plotly, you can easily fit a trend line. I fit a trend line, and the slope of that trend line is, boom, 3.08 meters per second. I mean, come on. It's almost like I expected that to happen. I mean, I'm pretty impressed with that. So that agrees with my experimental data. But wait, there's more. So now we can do it another way. So this is the finite difference method to model a moving string. So here's my string. I'm going to break it into finite elements again. And then these are evenly spaced in the x direction. So again, we're making the assumption that the vertical motion is very small. So the spacing, these only move in the vertical direction, and the spacing, the delta x spacing stays constant. And then I can label these 0, 1, 2, 3, 4, 5, 6. So they all have an element. And then x0, x1, x2, so forth like that. You get that. Okay. And then they have y values too. And then they have a mass, delta m, right? Because that's the same thing we did before. M delta x over L, where m is the total mass. And that's the linear density mu times delta x. Okay. Oh, that's a little arrow that they just move up and down. Okay, so here's 3 elements. yi, the one before it's yi minus 1, I gave them all indices, and then the one after it's yi plus 1. So there's my wave equation, and I need to get this in terms of finite difference. So it turns out, and I'm not going to derive this because I've done it multiple times, that the second partial derivative with respect to x can be written in terms of the element before it, the element after it, and that element. And so this is the second derivative as a finite element. Kind of cool. But wait, they also have to have an indice with time, right? Because if you think about this a little bit later, they have a new position with time. So the ith element has to have an indice to describe its time too. So each element has a position element I, and then a time element k. So these are all at the same time, so they all have the same time element indice k, k, k. Okay, so that's, and then if we have that, then I can write my wave equation, which is this. We've already derived that. I can write an expression for the partial derivative with respect to position as that, which I already did. Notice that it has the k in there now. I got that k. So I have I and k indices. And then I can do the same thing for time. Time is the same thing, right? Except instead of changing my I values, I'm changing my K. So these all have the same I indice, space indice, but now they have a different K index. So K minus 1, K plus 1, and K. And then we're divided by delta T squared. So if I put those two together, I get this is my wave equation with two finite differences. So here's my time derivative, second derivative with respect to time, second derivative with respect to space. And what I want to do is to solve this for the ith element in space the next time, right? So that's the future element. So if I could go through each element and find out what its new value is going to be. And this is complicated. I got another slide on this, but this is important, so it's got a box around it. So you notice that ik plus 1 depends on ik plus 1k. Is that a comma? That's a period. That should be a comma. And then I minus 1k, ik minus 1. And then these are all just constants. I put all the constants together. Okay. So here's the plan. Create three. We need three lists. Okay. I'm going to call it f old, the old value, f now, the current value, and f new. And that's going to correspond to k minus 1, k, and k plus 1. So f old is k minus 1, f now is k, f new is k plus 1. And then I'm going to pick values for f now and f old to start off with, because I need that to calculate the new versions, right? Those both show up in my finite difference. And then I'm going to find a new value for f each. I'm going to go through each one and find new values, and that's going to be my f new. And then I can move everything back and forth. I can make the now old and the new now, and then find the new. Okay, now I also want to take that one in and not have it fixed. I'm actually going to manually move that to make my little wave pulse, just like I did with the mass on a spring. Okay, so this whole idea of a list is kind of confusing, so I wanted to kind of plot it out for you. So here's just a few elements, 1, 2, 3, 4, 5, 6. So this is my old values, right, in the previous time, and these are the y values. So this is x, x, x. These are the x values that way. So here's I 0, 1, 2, 3, 4, 5. That's 6 elements. And this is at k. Let's call this k equals 0. Right there, I need a time index c too, so let's call it k equals 0. Now I can do the same thing for now, right? And it could be different values, it doesn't really matter, but they all have an I value, and these are at a different k value. So this is k equals 1. Now what I want to do, I want to use this equation, which I showed you before, to find the new value at each of these locations. Well, not the ends. I don't want to do this one or this one. I don't want to do I0 or I5 because I0 doesn't have an element before it to use, right? I'm going to manually move this one, and I'm going to keep that one set. So here's my new f, and I just changed them generically, but I want to show you where these terms comes from. Let's imagine that we're looking at this term right here, the I equals 1 term. How would I get that? Well, if I look right here, well, this is set, and that's set. So I'm not going to change those. I'm either going to not change it or I'm going to move it based on that wave pulse. So this term right here, the I plus 1k, so that means to find that, I need to use I plus 1 is the term before it, after it right here, so it'd be I2, and k is just normal k, right? And then this term, I minus 1k, is the term in space before it right there. So that term is this, right, with the f now. It's now because it's k, and this is k, which means now, but I minus 1, which means the term before it. I know it's confusing. That's why I drew this diagram. Hopefully it helps. And then here I have ik. They both ik. So that means the k equals 1 and the current element. And then here I have ik minus 1. So k minus 1 means the term, the older list. So the k equals 0 list, but the same element, right? So that term right here is that term right there. Okay, so then I can, but they're all just numbers. So I can use that to calculate all my numbers and get my new values. And that's how the finite difference works. Okay, let's get into it. So this is just the setup stuff. I have dx, which is spacing. dt is the time space. L, r equals 1 is, I actually didn't use that. Tt is the tension, the linear density. that's just, it's just a trick. That you can delete. I use that one. Now X is my X values, right? All my pieces in my list have an X value. So I need to start with an empty list. I go through and I just add a bunch of X's in there. Here you can see my 3 list. I start off with them empty, and then I just go through and I put them all at 0. I go through, they all have 0, 0, 0, 0s, but I have to put those zeros in there. This is the same stuff I had from before, my amplitude, angular frequency, amplitude again. I don't know why I did that. The time of the pulse, and then Fi. I don't know why I did that. The same thing up here. Okay, well, it works. Okay, so here's my t equals 0, and then I do a loop. So this f now 0, f old 0, f new 0, that's that first element on the left. I set it equal to 0, but then I say if time is still during that wave pulse, then I set them to this new thing. So I'm moving them. I move all 3 of my lists. I move those. Okay, so that's my wave pulse. And I only do it if t is less than tp. F data is just to make a graph, right? So if you want to make an animated graph, you need a list of the data points, and then you just plot them all at once. For I in range 1, this goes through. This is it. This is the key. The new value for each element. That's that differential equation. That's that finite element equation right there. I just typed it out. That's all. This now for I in range 1 to length. This takes the old values and sets them to the now values. So I move everything, shift everything over. Once I calculate the new values, my now values are now my old values, and my new values are now my now values. That's what these 2 things do right there. For I in range, this makes the graph, and then it updates time. And here we go. You ready? I mean, that's pretty cool, right? It's pretty cool. But what's the wave speed of the pulse? Well, I can do the exact same thing. I have to change my function around a little bit, but here's what I get. That's my plot of the position of the peak wave as a function of time. And look at that, 3.08. So I get my video analysis, the real velocity of the string I'm reviewing here, 2.85 meters per second. Cool. The theoretical based on the tension and the linear mass density, 3.07. Okay, that's pretty cool. The mass spring, 3.08 meters per second. That's pretty good. And the finite difference, 3.08. And I put the 2 there just to show you that it's actually different. But, you know, I'm just trying to show you. So that's that. So what do you think? Now, I do have one more string thing to do. So I will make one more string video. But again, I'll include the playlist for all my waves on a string videos, including the derivation of the wave equation and building this other stuff in there. So I hope you enjoy that. I've enjoyed it. I've got one more video left. I do have to do another experiment, so it may take me a while. But I do want to do this one more video before I forget everything. So hope you enjoyed that. I sure did. This is the part that I really enjoy, though. Okay, so I'll talk to you guys later. Oh, where's my stop button? It's way over here. Okay, stop.